Welcome to another episode of Machine Learning Made Simple. Today we're diving right back into the agentic frameworks, one of the most fascinating areas and happening areas in AI right now. And if you caught the last episode, you already know that the agentic AI aren't just a theoretical concept anymore, and they have been applied in multitude of enterprises and big corporations. They are out there actively solving real problems, optimizing workflows in big companies, and even reasoning through complex tasks. Something just which a few years ago would have seemed impossible outside of a sci-fi movie. But today we're going to dive a little bit more deep. See, in the past, AI agents were basically just rule-based systems. They could handle tasks, sure, but only if someone had painstakingly hard-coded every single step for them. Think LangChain. Now, they weren't adaptable, they weren't very flexible, they're very rule-based, and they'll follow those rules that have been coded by the programmers, the machine learning engineers. They're like very obedient robots that followed instructions but really couldn't think for themselves. And 1 year ago, that was the situation, and fast forward to now, and everything has changed. These AI agents have become way more dynamic. Now, instead of one regionally programmed system, we have swarms of agents that can work together, communicate, and even reason through problems like human team would. Instead of being a single agent locked into a single task, they can now distribute their work like an orchestration agent. They can be a dean agent, or there can be a foreman agent who can distribute the work to multiple of sub-agents who can work in tandem and optimize decisions. They can chat with each other. So you can have a whole team of AI agents that can work like a proper human team, and they can optimize the decisions in real time and collaborate like human teams do to solve problems much faster than a human could. Now, are they going to replace humans? That's a topic we're going to come to a later episode. But for now, let's just see how this is all evolving. So let's be real. This is not just some abstract AI concept. This is practical. Think about how much time you spend doing research, whether it's looking up the best phone to buy, finding the right investment strategy, or even booking a flight. And if you're an over optimizer like me, that would take on upwards of hours. And yeah, some of my friends says like that doesn't take that long, but if you are an over optimizer like me, then you'd know what I'm talking about. You have to look at every model of that phone and compare all the features and minutely decipher and what phone is best for your needs. For example, whether the iPhone is the best, iPhone Pro Max is the best, or if the Samsung latest generation is the best. Looks like if you're into astrophotography, then the latest generation of the Samsung phone would be best. But then if you're into Instagram pictures and those kind of social media posts, then the Apple phone. So these minute comparison really takes our time. So now you can offload those decisions to the AI agents, not all of them, but some of them. You keep some to yourself. Now, if you ever had to book a flight while trying to balance price, timing, and convenience, you know it's a nightmare. You start looking at flights maybe a few weeks ahead, and at first you see decent prices, but then you wait a day and suddenly boom, the price has jumped $50 or even more. And then the next day it has doubled in price. Like, why? Because the airlines are dynamically adjust prices based on demand, and the repeated searches, yeah, they're contributing to the price increase. They might think like, oh, it's coming from this different people, but it's really the same person doing so many searches. So what do most people do? Well, some spend hours comparing sites, switching between Kayak, Google Flights, Priceline, refreshing pages, adjusting filters, playing the waiting game. Others, they just throw money at the problem, pick a flight in 3 minutes and call it a day. Well, if they have money, they can do it. But what if you have an AI agent that could handle all of this for you? Imagine you enter your constraints, departure city, the destination, your price limit, no red eyes, no long layovers. And it also, of course, must between our travel dates. Let's say I'm flexible. Maybe I want to travel between certain dates, but some people are not flexible. For them, this will not work, but flexibility helps in the price being more malleable. So once we feed all these constraints, once we enter on this constraint, and then instead of spending hours refreshing the pages, the AI agent team can do all the work in the background. So we don't have to worry about that. It just doesn't check one or two websites. It scans every possible booking platform, tracks price fluctuations, even predicts whether prices are likely to go up or down. And when it finds the best match, it either alerts you instantly, or if you have given it permission, it books the flight for you. So that's the power of agentic AI. It turns what would have been an exhausting time consuming process into something that happens almost instantly. Or it doesn't happen almost instantly. The AI agents are running in the background. We just don't have to spend any time doing it. And that's just one use case. Agentic AI isn't just about making travel easier. It's reshaping industries. In our last episode, we touched on how these AI systems are already transforming finance, e-commerce, and customer support. But today we're going to go even further. We're going to ask some big question. Where did these AI agents come from? How did they evolve from simple rule-based systems to something capable of real reasoning? What is the next leap in their development? And what does this mean for businesses, consumers, and even entire industries? Because here's the thing. This shift isn't just happening in isolated pockets, it's happening everywhere. One area that's about to see massive disruption is networking. Right now we're living in a 5G world, but what about 6G? That's just around the corner. And AI agents are going to play a huge role in shaping how the next gen networks are operating. Think about it. Right now, networks are still mostly managed by humans. Engineers monitor infrastructure, they optimize bandwidth. Yes, some have automated circuit breaking and all those things, but most of the routing is done by electronic equipments. And all those troubleshooting issues that they arise are still managed by a human agent. So that adds a lot of time. Think about when you have to switch to a new network, or when you're roaming, you have to call and turn on your roaming, and that takes some amount of time. How about making that fully automated? And we're going to talk about that. But with these AI agents, the entire process becomes fully autonomous. So when your device, your networking device or your phone moves from one network to another, the integration would be fully seamless, because when your phone moves from one network to another, so the settings needs to change. And usually what happens when you ask for roaming, those settings need to be manually inserted. And that some networks have optimized the system, they have codes running which can automatically inject that, but many networks fail to do that, especially if you're traveling internationally and let's say you're on Verizon and you go to Vodafone in India. So those networks may or may not talk to each other. So then you have to manually enter the configuration in order to enable roaming, international roaming, or otherwise they might have, your Verizon has good tie, most of the networks have good tie-ups in other countries. Let's say you're traveling in some remote country which doesn't have networks who have tie-ups to your network. So there you have to do it manually. So with this new 5G system, this whole process becomes fully automated. The device moves seamlessly from one network to another. Imagine a network that can adjust itself in real time, routing data more efficiently based on the traffic patterns, detecting issues before they even happen, and optimizing speeds without any human intervention. So that's just not for 6G, that can also happen to broadband, and that's where the main innovation are coming. These AI agents can act as switches to route data more efficiently. That's where the things are headed. And it's not just a nice to have feature, it's going to be essential. With the rise of edge computing, IoT, Internet of Things, and increasingly complex data flows, manual network management just isn't going to cut it anymore. AI agents will need to step in to handle the complexity. But of course, with great power comes great responsibility. So we have to ask, how do we ensure the AI agents remain reliable and secure? What are the risks of letting AI control something as critical as network infrastructure? Think Matrix. How do we strike a balance between automation and human oversight? And that's what today's episode is all about. We're going to explore the history of agentic AI, how it evolved, and why it's suddenly accelerating so fast. Because if you're someone who likes to connect the dots, you already know history matters. Looking at past trends helps us predict where things are going to go next. For example, we have already seen some early missteps with the AI agents. Issues like hallucinations, faulty decision making, and unintended biases in reasoning. Understanding those failures is just as important as celebrating the successes, because if we don't, we risk making the same mistakes all over again. And here's something even more exciting. AI agents aren't just improving automation, they're changing how we process knowledge itself. Ever heard of retrieval augmented generation? It's one of the most promising advancements in AI today, and guess what? It's now being supercharged by AI agents. Instead of just retrieving information, AI systems can intelligently synthesize, analyze, and structure knowledge in ways that mimic human reasoning. But that's a whole other rabbit hole. In fact, it's so big that we're dedicating an entire episode to the retrieval augmented generation in the near future. So watch out for that episode. So here's what coming up in today's discussion: the evolution of agentic AI from simple scripts to fully automated reasoning engines, real world use cases. So go beyond the hype, how businesses and industries are actually deploying the systems, and the next frontier of AI powered networking, how agentic AI is about to transform connectivity as we know it, and of course the risks and challenges that come with all of this progress. So if you missed the last episode, go check it out. You can find it on Spotify and Amazon Music and YouTube, both audio and video version. But for now, let's dive in. We're starting from the beginning, the genesis of AI agents, how they evolved and where they're going next. So in the next segment, we're starting from the beginning, the genesis of the AI agents, how they evolved and where they are going next. So let's dive in. I consider the main genesis of the AI agentic framework started with Hugging GPT. And the whole idea behind it was to take the ChatGPT model, which at the time was running the GPT-4, and connect it to the Hugging Face models to solve more complex problems that ChatGPT simply wasn't capable of handling on its own. It was not fully multimodal. It was great at text-based tasks but couldn't process images, audio, or structured data the way newer models can. For example, back in December of 2023, if you give ChatGPT an image of zebras and giraffes roaming in the savannah and ask it to describe the image and count the number of animals in it, it wouldn't be able to do it because it had no built-in vision capabilities. It was not multimodal and it was not trained to process images. So it had zero chance of providing an accurate response. But the researchers behind Hugging GPT had a different idea. Instead of just expecting one model to do everything, what if you could break down the problem and assign different model to solve the different sub-problems and then combine the results? For example, take this image of this savannah which is filled with zebras, lions and giraffes, and instead of expecting ChatGPT to magically analyze it, let the system call in specialized AI models to help. It can call object detection models like DETR, which can count animals in the scene. It can call image captioning models like Blip or GPT-2 image captioning, which can generate meaningful description. It can call the vision transformers, which could extract semantic properties, helping describe the scene in more detail. Each of these models could work independently on their specific subtask, and ChatGPT would then gather all their outputs, process them, and generate a final response. So ChatGPT becomes the AI agent who is responsible for deciding which models to call and how to integrate their responses. And here's the AI agentic framework is starting to build. And this is what made Hugging GPT so revolutionary. So instead of relying on a single AI model to do everything, it treated AI models as a team of specialized agents where each agent has its own role in solving a complex problem. So Hugging GPT wasn't just another AI model, it was something different. Instead of trying to make a single AI system that could do everything, it took a completely new approach. It treated AI models like a team of specialists, each responsible for different tasks, and put them together in a way that made them work as one. Think of it like this: before Hugging GPT, if you needed an AI to do something complex, it mostly was a one tool at a time process. The AI would recognize a task and call a single external tool to handle it. Simple, direct, but limited. But Hugging GPT, it stepped things up. Instead of just handing off a task to a single tool, it will break the problem into pieces, find the best AI models for each part and get them to do their jobs, and then pull everything back together into final complete answers. So let's go through what the process actually looked like. First, task planning. Hugging GPT had to think through the problem and break it into smaller pieces. If you asked it to analyze an image, for example, it had to figure out exactly what needed to happen, maybe object detection, maybe image captioning, maybe even some kind of reasoning about what was happening in the scene. Next, model selection. Hugging GPT has access to the entire Hugging Face model hub, which meant it had thousands of AI models to choose from. But not all models are created equal. Some are great at detecting objects in photos, while others are only good at scanning text in documents. For example, realize that it needs to detect objects. Now it had a few DETR models, the object detection models that it's disposal in a search, it came up. So the DETR are the object detection model. Right now you probably have heard of YOLO, you only look once. That is also an object detection model. They kind of fuse their architectures together, and we covered in an earlier episode. So let's say it has looked at, the Hugging GPT is looking at few DETR models and needs to select what is the best DETR model. Now for example, it looked at the Facebook DETR ResNet model, which can perform object detection and a variety of object detection. It also is looking at another DETR model which just performs in-document table detection. So obviously in-document table detection is not great for the use case of detecting giraffes in an image. So now the model will realize, okay, let's select the Facebook DETR ResNet model. That would be the ideal model, ideally suited for this use case. So the model selection is big thing. Of course, it's going to augment its knowledge with VIT, the vision transformer, which also helps it in understanding the image so that it can perform the model selection better. So after the model selection, picking the right model. So picking the right model for the job is a key part of the success, and then task execution. Once the right models were chosen, Hugging GPT would send the data to each of them and let them do their thing and collect their outputs. And this is kind of complicated because the reason is the way to communicate with these models have to be through very structured inputs and outputs. And due to the stochastic nature of the GPT models or any large language transformer models, transformer-based models, and due to the stochastic nature of the transformer-based models, those exact responses, input-output formats might not be respected during generations. A way around it is to use LangChain, which can force those exact responses by using pydantic models, and that's a technical topic we don't want to touch, but that's the whole idea. There's some technical issues in sending the models, sending the queries to the models and getting the outputs in the required formats, but that is usually taken care of by using those technical backends. Finally, response generation. ChatGPT would take all those results, piece them together and generate a final human readable answer. Now at first glance, this might sound a lot like Toolformer, which was another AI system designed for tool calling, but there is a key difference. Toolformer was built to call external tools only when needed, like using a calculator for math problems or an API to check the weather. It was a step forward from the older AI models, but it still worked on a single call, single response basis. And also that Toolformer tool calling ability is actually hard-coded into the large language model. In fact, the large language model has to be fine-tuned, which means you have to create a new large language model on top of the existing vanilla large language model just for the tool calling functionality to be embedded. Hugging GPT, on the other hand, uses a vanilla large language model and thus uses its own inferencing property to connect all the dots and find all the models at inference time. By inference time, I mean no extra large language model training required, and that's the prohibitive step. Like, training a large language model is a very, very expensive process. Most people, in fact, very few people can actually afford to do that. So this is really the next stage of AI revolution, where we don't actually fine-tune the large language model for every task we want it to perform. We make it versatile by putting another layer of this tool calling functionality by adding them, appending them, using all these agentic model frameworks. So that's where the agentic framework started taking shape. So this might sound very straightforward, but there's what got tricky. The model selection part was slightly tricky. Let's say Hugging GPT needed to perform object detection. It had to pick between different models, and that was not as easy as it sounds. You might have two models that both say DETR in their name, but they do completely different things. For example, one might be interested in recognizes animals in images, and one model might be very adept at recognizing animals in images, and the other one might be only good for detecting tables in documents. And pick the right one, and suddenly the AI is completely useless for the task at hand. And that's why Hugging GPT had to be smart about how it selected models. It needed to understand the problem, understand the available tools, and match them together correctly. Once the right models were chosen, the system could send the inputs, get the results, and pull everything back together into a complete answer. Now, at the time, which was December 2023, this was cutting edge research. Back then, ChatGPT wasn't fully multimodal yet. It couldn't process images natively, and its reasoning capabilities were still somewhat limited compared to what we have now. And that's why Hugging GPT was so important. It showed how AI models could extend their capabilities by working together instead of trying to do everything on their own, like fine-tuning a large language model for tool calling like Toolformer does. The versatility of the LLMs were brought into the forefront, and we now started to realize December 2023 was not very long ago. It's like almost only a year ago. Then people started to realize that large language model doesn't need to be fine-tuned every time. We can just use that model, the basic vanilla simple base model, and then we can build those arms and legs around it and make them agentic. So that's the whole point of the agentic framework. And here's the one thing. 1 year and 3 months later, this isn't just research anymore. This agentic AI approach is now shaping the entire field of AI. The idea that a single model should do everything, that's starting to look outdated. Instead, we're seeing the rise of these multi-agent AI systems where different AI models work in tandem, each specializing in different tasks. And Hugging GPT, that was the first major step towards making that a reality. It introduced many things. It introduced the ability to break down problems into subtasks, dynamic model selection to choose the best tools, and a multi-agent framework where different AI models could collaborate. Now, Hugging GPT was a major step forward. It showed that AI agents could work together, delegate tasks, and extend their capabilities by calling specialized models. But that was just the beginning. In the next segment, we're going to explore how this concept is pushed even further. We'll look at how modern LLMs are becoming more self-directed, how they're integrating real-time data retrieval to enhance decision making, and why we're now witnessing the rise of autonomous AI research assistants, systems that just don't fetch information but actually analyze, refine, and generate insights on their own. So stick around, because if Hugging GPT was the first step, Agent E will show us what's possible next, and trust me, what's coming is even bigger. Now let's talk about the tool that first brought the agentic framework into the mainstream by demonstrating that AI agents can successfully interact with their environment and solve real-world tasks, and that tool is called Agent E. If you have been following AI automation, you already know that autonomous web agents have been around for a while, maybe a year or so. But before Agent E, most AI-driven web navigation systems were fragile, inefficient, and unreliable. They could follow simple instructions, but often they would get lost in the complexity of the real-world websites. Now, AI Agent E changed all that. For the first time, it did prove that AI agents could not only navigate the web, but also plan, adapt, and correct themselves, and just like a human would. And that's why the system is such a big deal. So today we're going to dive into what makes Agent E different and how it is built and how it outperforms every web agent before it. Let's get into it. At first glance, you might think web automation should be easy. AI can read a web page, click buttons, and enter text, and it's just interacting with the browser, right? There's so many browser interaction tools around. There is Selenium and others. Why should it be so hard to build an AI agent just to use Selenium to interact with the website? That is not entirely correct. Web automation is actually a nightmare for AI agents. Why? Because websites weren't designed for AI. They were built for human beings. In fact, the current breed of websites, the code that actually doesn't immediately translate to the visual elements that we actually see on the screen, because they're content delivery networks dynamically injecting all those contents that are processed runtime. For example, let's say an AI agent is trying to book a flight. Here's what's going to happen. It will load the page, but the HTML would be a mess, full of hidden elements, ads, and unnecessary scripts. The date picker wouldn't work. The date picker, for one, doesn't really work like a simple text box. It's like a dynamic UI element. So forget about the AI interacting with the date picker. It's one of the hardest things to interact with. What is simple for a human being to interact with is almost impossible to interact with by an AI system. And even though if it end up selecting the date, a pop-up might appear, which is something that AI wouldn't expect. And all these curveballs that gets thrown at our way at every step on with dynamic websites really trips up AI agents because they like clean systems. Yes, it can interact with the early 2000, any web page built in the early 2000, but the modern UI is too complex for AI to navigate successfully. And the worst of all, prices change dynamically based on demand, and meaning the AI strategy has to be adaptable when it's trying to book a flight. Or older AI agents couldn't handle this situation. They would either fail completely, get stuck and stop working, and hallucinate success and return a wrong output and repeat actions indefinitely. So this is why web agents have been notoriously unreliable until this agentic framework came along. So let's see how Agent E solves this problem. Agent E introduced something known as a hierarchical agentic framework, which is just a fancy of saying it separates planning from the execution. And here's what that actually means. It has a planner agent, which is the brain, and breaks down the task into smaller steps. Think about what Hugging GPT was doing, the same thing. Like go to the website, find the search box, and or click submit. Okay, so these are the steps that the AI agent needs to do in order to complete the task. So the planner agent breaks down those steps and then sends each of these steps individually and makes sure that steps are complete before moving on to the next step. So there is an iterative process there. And the other part is the browser navigation agent. So the hierarchical framework has two main agents. One is a planner agent and there is a navigation agent, browser navigation agents. This is the hands. It follows the plan, interacts with the websites, and executes the steps. So by splitting these roles, Agent E essentially reduced the complexity and made better decisions in real time. The planner doesn't get distracted by the UI noise, and the navigator focuses on getting things done efficiently. Now note that this is where the clear separation roles are coming, and this is clearly a major step forward in the agentic framework, where if you have used Creo AI, then you probably have noticed that in Creo AI, each AI agent has a very specific defined role. And if one agent is doing one role, a research role, that AI agent will not worry about the grammatical correctness of the output, while one research agent will not interfere with the work of the proofreading AI agent. So the same thing here. So, and all this concept came from the demonstration that this Agent E framework provided. The Agent E framework provided that separation, even though the separation was there before. It clearly showed by this hierarchical separation of roles, the task can be performed with much higher fidelity because one agent doesn't get confused by the noise from the other agent task. This is just like a specialization of roles, that in a team we have different people working in a team, and each person's strength augments the team's total success, but each role doesn't interfere with the other person's ability to do the work. So just by splitting these roles, Agent E reduced the complexity and really improved the accuracy. And here's where it gets really smart. Agent E just doesn't follow the instructions blindly. Instead, it uses something called change observation, and the change observation is very crucial. And change observation is something we know in refined framework. If you have listened to our earlier podcast, the change framework is essentially where you iteratively refine your output. So let's say the LLM gives an output, and the refined framework verifies the output and sends it back to the LLM if it doesn't pass a threshold of refinement. And then there are variations on that. There is reflection framework, there is React framework, which all of those involve a certain degree of autonomy and tool calling. So essentially the idea is simple. It's self-verification. LLM gives an output, quality of the output. I mean, if it's not that good, then it gets fed back into the LLM to refine it even further, and the history keeps growing. The LLM keeps seeing its previous responses. It's like teaching a child the first answer. What is x plus 2 equals 5? The child says 2. It's like, that's the wrong answer. What's your thought process? Give me the thought process. It's like, I see 2 on one side, it goes to the other side. It's like, that's not the right answer. So think again. You started with 2, so that's the wrong answer. Okay, so then the child thinks, okay, I'll subtract 2 from both sides. Okay, so that's the right step. So in that process, what we're doing is giving whoever is learning the algebraic solution the previous feedback so that they can learn from the feedback. It's the same as the refined framework. The refined framework essentially ingests all the preceding history of failures and slowly iteratively improves on it. And the same thing here. So let's make it more concrete. Let's say we want to find out what is the pricing on Canva. Canva is where we can go and build our LinkedIn banners, build our logos and all that stuff. So we want to know what is the pricing of their business model. So if we give the AI agent the task, so the planner agent will first think, what is the first step? the first step would be, of course, go to the Canva website. So the first step, it will say navigate to https canva www.canva.com and see what response we get. So the planning agent takes that command, navigate to canva.com, and gives it to the browser navigation agent. Browser navigation executes it, goes to the website, and feeds back whatever it sees back to the planner. It's like, okay, we see we're not on the Canva web page, and the current URL is canva.com. If it fails, then it will loop and see if the proxy is not working or not. So let's say we go to the Canva website. Then what is the next step? So the next step is the planner agent will think, okay, we are at the Canva website. What would be the next step to find the price, the pricing model? So now the question is there a link or a section labeled pricing or plans? And it takes that action item and gives to the browser agent and asks it, find a button or a section which says pricing or plans. So then the browser agent does its things and tries to find it, and says, then sends back the response, yes, I did find a section which is labeled plans or pricing. Would you like to navigate this section? And then the action planner agent realizes, okay, we did find a pricing page, so maybe we should navigate that. So it sends back command, navigate to the plans and pricing section, to the browser agent. Browser agent goes to the navigation and navigates that page and extracts and scrapes that page and sends back all the pricing element. So it said the response can be, I clicked on the plans and pricing button. This opened a drop down menu. From there, I clicked on the compare pricing link, which redirected to the detailed pricing page. So all those details that it sees, it sends back to the planner agent. Now the planner agent has to decide what to do next. The planner agent might ask, is there information available about the Canva Teams subscription, specifically about the price and the minimum number of users required? So that's what the user questioned, like what is the business pricing of the business plan? So now the planner agent asked the browser agent the same question, do you see anything on the pricing page for the business use case about the business teams? And then the browser agent does some navigation, scrapes the website, and sends back the information that it found, that the Canva Team subscription is priced at blah, blah, blah. And then the planner agent realized, okay, I have reached my end goal. I'm good. I can return this answer to the user and say, okay, I have found the Canva business plan is costing this much, and sends it back to the user. This whole interaction, you can notice how many steps it took, and human being perform all these steps very fluidly and almost one after another without even forethought. But we are, in our brains, are making all these decisions and choices, where to go next, which button to click next. See how many interactions these two AI agents had to communicate between each other just to arrive at the final answer. This is pure agentic framework communication, and this is what really makes the agentic framework tick. And we're going to talk a little briefly about this. And it turns out that the more the AI agents communicate between each other, the higher the quality of the output, and that's seen in other agentic frameworks like ChatDev, and we're going to touch briefly on that. But for now, let's just focus on Agent E. So this is the first time an autonomous agent was able to successfully navigate a web page just like a human being. And the reason is the separation of the agentic roles. One agent is just planning, one agent is just dealing with the browser noise, because there's tremendous amount of browser noise that the agents have to deal with. And there are more nitty-gritties about what are the key principles that reshaped the agentic AI. Those details we're going to leave for another video segment, which is just for this specific paper. Keep an eye out for that video on our YouTube channel. But for now, we'll just mention that this was a monumental step towards fully autonomous AI agents interacting with the environment. So inspired by Agent E, there are a few other autonomous agents that are out there now which can interact with the environment directly, not just web agents. There are agents which can interact with the full OS. So one of the famous one is the Claude's agent that probably came out soon, and you probably heard about it. It made a big splash. It was kind of based on Skyvern, which we'll also look at quickly, but this autonomous agent was released by Claude as a part of the API. What it does is that if you give it a task, it will look what is there on your screen, and you can ask it like, okay, find me this vendor and the details of this vendor, its company name, its email, and whatever else you can find, and fill out this vendor request form that I have on my screen. So Claude goes through a set of things, whatever it sees on the screen. If it sees a browser, then it will go in the search the browser for the vendor and try to scrape as much information as possible. Now if it sees the vendor request form on the screen, it will just enter the data in there, and that's done. Now let's quickly talk about Skyvern, which really motivated all those agentic frameworks from Claude. Skyvern is mostly like the web, like the agenty that we looked at. It's mostly a web interacting agent. It will interact with web elements, different web pages. For example, a very specific task might be go to the Yahoo Finance website and then find the Apple prices, the Apple stock prices, and scrape the live data. If you run the program, you'll see that it will go to the website, scrape the stock prices, and then load all the stock prices live, all the live data. You can actually perform this live, like when you check your stock prices, then you'll extract all the information and then collect it and give it back to you in a structured or unstructured format. You can decide what structured format. You can have it in a CSV format, or you can have it in a JSON format. You decide what output format you want. Now, this can be superseded and made it more enterprise grade robust by using LangChain, which we'll cover in a different video when we do a more deep dive into creating agents, AI agents. So look out for that video on our YouTube channel. Now let's talk about a more automated approach, a more drag and drop approach. While Skyvern is slightly needs tinkering with, but it also is free. Claude's was not fully free, but it's also automate most of the things, and it can only interact with the elements that are on screen. So it has its own niche of working. But with AutoGPT, you can ask, hey, take this YouTube video or the list of YouTube videos and transcribe each of them. So you can create the entire agentic flow where you can tell the agent to go scrape that YouTube video, transcribe it or convert that to MP3, and then transcribe it with a model, and the agent will do exactly that. So, and all of that is fully automated in a drag and drop fashion. So those are the use cases. If you're really hands-on, then use Skyvern, and it's open source and you don't have to pay anything, but you have to work a little bit to make it work. And if you really want drag and drop approach, use AutoGPT. It's probably a high price. You have to check the price. It might be costly to run the whole agentic framework on AutoGPT. Claude's model, I personally would not use, because I feel it's a violation of privacy to give the full control of my screen and my operating system to an AI agent. It can do things that I cannot even see. So it's better to stick with one of those options. For full hands-on, use Skyvern. For full automated drag and drop approach, use AutoGPT. And if you want to build enterprise grade product, then use LangChain. We talked about AI agents navigating the web in the last segment, how they can interact with websites, process dynamic content, and even correct their own mistakes. But web browsing is just one piece of a much bigger puzzle. The AI agents are doing much more now. Imagine taking the same agentic AI approach and applying it to something far more complex, like the entire global communication network. That's exactly what's happening with the rise of these AI-driven 6G networks. Instead of just responding to user requests or fetching information, this new AI agentic frameworks are actively managing the flow of data across the world, deciding what the bandwidth should be allocated, how to prevent congestion, and even optimizing energy use in real time. And that's the kicker. Energy grid system will be far more optimized by the use of these AI agents. To understand how this shift is happening, we're going to look at a few key papers that have come out in recent months, in fact in the same month of February of 2025. So these are called Advanced Architectures in Communications, which are integrated with agentic AI. So we're going to go over that and break it down. The current generation, the 5G network, is still based on electronic routing, But the next generation 6G networks should be and probably will be based in this AI-driven network agents routing. So most of the task and the backend hauling would be done by agentic AI workflows, like autonomous agents managing the workflow in real time. No amount of electronic routing can even compare with that amount of autonomous decision making, because all the electronic routing has to be hard coded ahead of time. If a server goes down, if something breaks down, those electronic circuits can only shut down that portion of the network, but there is a human agent can go and fix the load balance and whatever is wrong with that part of the network. For example, let's say our router has only a 2 megabyte cache and someone is using that as a web server. Guess what? The router, if gets like 1,000 requests at the same time, the memory will be overflowed, and definitely the web server will stop responding. In that case, the AI agent can go in, totally unclog the cache. So the first thing the AI agent will do, it will look at the logs and decide, okay, so the browser memory has overflowed because of so many server requests. So the first thing I'm going to clear the queue, because the computer is not able to handle the massive influx of requests. So let's say the browser queue, server queue is full. Let's say there's 1,000 requests pending. It fulfills one request. Immediately another request comes in, and it doesn't give the CPU any break for the router. So the only best thing would be to manually reset the router. That's what we usually do if the router misbehaves like that. There's no other way to clear the cache. Now an autonomous agent can come in and dynamically remove. First, it will disconnect the cache that is continuously overflowing the memory. First, it will disconnect it, and then it will clean the memory and reset it live in real time without any human intervention, and then let the cache flow in sequentially without overloading that specific server. So that's a very small, tiny example, but that's how it can act. Complete autonomous intervention for any kind of blockages in the network. And that's what people are thinking about, to implement these autonomous agents to improve the network. And people have come up with different ways of doing this scaling. And there are a few ways people are doing this scaling, and some of it's already in place. One of the main differentiator is that now they're going to separate the devices and the network into 3 different planes. So there will be edge devices which are consuming and interacting with the network, and the network itself will be separated into 2 different planes. One is the user plane, where the user data and packet forwarding, all those network functions are working, and then there is a control plane which will control that flow between those edge devices that is consuming data. For example, there is an IoT device, your smart thermostat. It's reading all the temperature in the room and sending back to the servers for feedback. So that flow goes from the smart thermostat to the router, and the router connects to the internet, and then it goes a few hops and then goes to the server. And all that intermediate processes can be broken down into a control plane, and there would be AI agents would be controlling the flow. So during times of high congestion, especially when the temperature is rising fast, let's say 10 million thermostats started sending volumes of data to the server, and it realizes the server is about to crash. So what it does, it slows down a few of the packets. So it routes a few of the packets. It's like, let's slow it down. Let's let it sit somewhere else in some other cache till these first few ones are going through, so that it doesn't overload the server. So it learns the server capacity over time and controls that. This is a very simplistic example, but this is how it's essentially going to work. So that differentiation, the control plane, which now is autonomously controlled by these AI agents, will really make a difference. Right now it's electronic, mostly the electronic switches, they detect the load and they automatically turn on and off, and that's how it mostly works. And then there's the concept of energy efficiency. It will be continuously monitored by the AI agents, and then it will figure out, okay, is it energy efficient to route through this geographic location. For example, it turns out a server, let's say in Phoenix, during the hot months of Phoenix, it's been running 24/7 because all the packets has been routing through it just because it just happened. Then the AI agent would realize that is not very even energy efficient because we have to cool the server as well, and it's handling so much load. Why don't we route some of those packets through Flagstaff, which is geographically close to Phoenix and at least 20 to 30 degrees cooler? So that will give the server in Phoenix a break and introduce only slight latency in the packets. And that's an amazing decision which a human can clearly make. But guess what? There's so many packets a human being cannot sit in front of a dashboard and all the times and make those decisions. An autonomous agent can make these decisions much faster. And this is not just for electronic communication. It can be also applied to other energy grids like solar farms and wind farms and any kind of renewable energy, where usually there's a lot of wastage, especially during non-peak hours when there is a lot of wastage, because it's more expensive to store that energy than distribute it, at least currently, because the batteries are very expensive. As batteries becomes cheaper, then storage would not be a concern. But right now, storage of power is so expensive that they usually waste it. And that's why Bitcoin miners usually co-locate in those near those solar farms to extract those extra energy, which can they get for almost nothing, because the solar farms usually throw away that energy anyway. So they get, those Bitcoin farms can get access to that almost free energy for like cents on the dollar. And if you look at the papers that are coming out, they are going even further. So they are saying that AI agents can be incorporated at each level. You can incorporate AI agents on your phone, which is an edge device, and is consuming and interacting, consuming bandwidth and interacting with the network and using the communication protocol. So AI agents can send data from those edge devices to the communication layer, and then the communication layer would be, the next step would be the localized agents on the router. So the AI agents would be on the edge devices, the phones, and then the AI agents on the routers, and then there will be AI agents, of course, on the cloud, which handles the all kinds of layer management and everything. So it will be a very complicated, and that would be the next stage. But right now, people are just envisioning how it's going to work. So there will be AI agents at every level. AI agents on our phone interacting with the router AI agent, and AI router agent realizing that, okay, that phone is probably not watching Netflix. It has higher bandwidth requirements. It will dynamically adjust. Right now, most routers can do that, but those are hard-coded. If it's agentic AI running on a router, then it can do it more efficiently. It can shape the packets, like it's called packet shaping, bandwidth shaping. It can shape the packets, means it can give more bandwidth to, let's say, a TV which is consuming more resources watching Netflix, and it can minimize the bandwidth available to, let's say, a smart thermostat, for example. So then the AI agent will take that from our local router and send it away to the communication layer. And there are so many agentic AIs just waiting at the communication layer, and they provide different functionalities. One AI agent can just reduce startup delays. Let's say there's a new user who signed up for, let's say, your internet, and if even 10 years ago, it was such a hassle to set up the router and connect to the internet, because you have to call and give them your modem's MAC ID and they'll manually turn it on. And all of that can be fully automated with this AI agent. All you need to do is scan it with your phone and you send it, and the AI agent will know there's a new user and the new user needs to be connected, and they perform those necessary steps to have those new users' MAC ID, router ID connected to the network, and perform all those necessary steps to disseminate all the permissions, record permissions at different places, at different nodes, which can now allow that router to channel through those different nodes. So that's one cold start function that an AI agent would be specifically designed to perform, just to onboard new users or new routers. And then there will be another AI agent which can perform dynamic resource allocation, like we talked before. It can look at high demand to certain routers and then reroute the traffic to some other routers, maybe from Phoenix to Flagstaff, just to get this server in Phoenix to cool down a little. And then there will be another AI agent which would be performing real-time monitoring, and then realize, okay, this server in Vegas is really clogging up, it's probably running out of memory, we need to offload it and let's send it to Reno, and something like that. And there will be another agent which will be looking at security protocols, and let's see which packets are really violating the security protocol or might have malicious content, and can perform all those. So that will be part of a support and compute layer, and this is called function as a service, because each AI agent is providing a function. These functions used to be initially, and still now, provided as hard-coded rules that are running on some server, or some part is actually still manual, like onboarding of new MAC IDs is still manual. So this would be fully automated, and each part that is manual or is rule-based currently will be fully automated by using AI agents. Each part would be a function that an AI agent will perform. So that's a function as a service, and that's in proposal stage, and we probably will see see it implemented in a few years already. So don't get surprised that everything becomes really smooth in your internet and communication. And another thing that caught my eye, and I already mentioned that, is the separation of the control plane. And what it does, it really allows the seamless roaming functionality. And especially if you have traveled overseas to a different country which has networks which really doesn't talk to your home network, and then you would know the roaming is a headache because you probably had to get new SIM card and enter the network details and all the hassle that are associated with that. Now with this new architecture, if the 6G is implemented and it separates the user plane and the control plane, then our devices just becomes nodes in the network. And then if there are two networks, then the nodes from one network will seamlessly move to another network. And what happens is that agentic frameworks can recognize another node, incoming node, and then transfer all the properties from the other network and blends that seamlessly. For example, if the properties I'm talking about is all the network connections. So if you go into your phone's network settings, you will probably see all the specifications, what is the closest tower and what are the settings for it, what is the network protocol to use, TLS, or what encryption algorithms does the tower use, and what kind of handshake does it use. All those settings are saved and they're usually pushed into the phone the moment the SIM card is added and connected to the network. However, when moving to another network, that process might not be automated because, as we talked about before, those rule-based triggers are probably not triggered because that's not a new SIM card that's being added to the network. So now with this new framework, when this SIM card or this phone or with an electronic SIM moves into a new network as a node, all those settings can be seamlessly merged into the new network by this agentic framework, because it's just one node moving from one network to another and just inheriting its properties. And if you think about it, it's just like a graph-based network. There's one graph and another graph, and when a node moves from one graph to another, it just inherits the properties of the new graph, and that it makes things so simple, so elegant, and of course really abstract. However, that's how it should be done. It make it abstract and it make it simplified at a level for it to use. And that's the next generation of the communication protocols that we're looking at, fully autonomous, fully agentic, and fully driven by AI. That's it for today. We covered a lot of ground, starting from the genesis of AI agents to autonomous agents, web browsing agents, and now the future of innovation, the 6G networks, the communication protocols, and using AI agents in the infrastructure. So we are now seeing infrastructure as AI agents, and that's the next generation thing to do with AI agents. That's the future. So that's it for today. We're going to stop here. See you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.